All right, let's start. So basically at frequency response, the first thing that we need to understand is Miller's theorem. Okay, so these theorems tell us that, so whatever prerequisite that you already learned, not really important, but just to get some concept last class. But now this is the important one. So Miller's effect, it says that any impedance between two nodes, okay, between input and output, if there's any capacitor or impedance in around them, that can be splitted into two individual impedance connected to ground. So meaning that if you have a circuit, input at X, and then you have your Z, maybe a capacitor, output at Y, you can actually split them into something like this. So you got X, and then Z1 connect to ground. You got Y, and then Z2 connect to ground. So you can have both parts, okay? So this Z1, Z2, they are all different. But when we change something, when we split the circuit, we need to make sure that they still look the same. They still have the same characteristic. So what characteristic that we need to maintain is, because they are in series, so we have to make sure that no matter how we split them, in the end, we need to ensure during calculation, the current is still the same. So we need to ensure that the current flowing to your Z1 is equal to the current flowing to your Z2, and it's also flowing through the current of your Z. So in this case, how do we do? You don't need to see up there first. You see this one. Okay. So you imagine what exactly is the current flowing at Z. Means V over R. Z is basically one type of resistor only. So V over R. What is the V? It will be Vx minus Vy over Z. This point minus this point over Z. Meaning that the voltage flow over the resistance. So this is our current. We say that this current supposed to be the same current that flow to Z1. So what is Z1? Z1 will be Vx divided by Z1. What's the current flowing at Z1? It will be Vx divided by Z1. Then using this formula, how do we find what is Z1? Z1, you just rearrange. So we move Z1 up, Vx, Vy move down, Z move up. So it becomes Z1 equals to Z over 1 minus Vy over Vx. And what exactly is Vy over Vx? It is output over input. So it is your gain. Therefore, your Z1, we can model Z1 into Z over 1 minus A. Or Z2, it will be equals to Z over 1 minus 1 over A. Our aim is to still follow this, but from here, it will be equals to Vy over Z2 already. Then we can get this equation. So this is a very important concept whenever you see something very complicated. You have to split the circuit. When you see something complicated, you have to split the capacitor. So you can split it this way. Just ensure that the gain is still the same. The current is still the same. Okay, I'll give 2 minutes to study through this to make sure you understand how do you convert from Z into Z1, Z into Z2. Or if you do not want to memorize that, do not want to know how it happened, you just need to memorize these two equations. Just take note that Miller's effect only happens from when there's a capacitor connected from input to output, not any point of it. Must be input to output. Okay, so there's one example over here. Let's say we have an amplifier. The triangle part is the amplifier. And then we have one capacitor connected between the input and the output of the amplifier. So there's one capacitor here. And we know the impedance for capacitor is equal to 1 over Cs. Okay, S is j omega. So 1 over j omega C. So we say that for this circuit, we can convert into C1 and C2. Now let's examine what will be C1, what will be C2. So from the equation, we say that Z1 needs to be equals to Z over 1 minus A. Okay, so if it is this case, what is our Z? Our Z is now 1 over CS. 1 over CS. So we take 1 over CS, and then it says that at the bottom needs to divide by 1 minus A. So this will be Z over 1 minus A directly already. Okay, because that is 1 over CS. Then what about C2? C2 is Z over 1 minus A minus 1. So it's 1 over A. So 1 over CS still remain, but now divide by 1 minus 1 over A. So you will realize something. Let's say our capacitance. Okay, so you will realize that, let's say our gain, okay, at over here is something big. Okay, so it's, let's say, negative 10. So 1 minus negative 10, so it's 11 already. We take this term as C, so it's around 11C. But if this is A is minus 10, 1 over minus 10 is something very small. So overall, this is only 1.1 C. So you can see that when we split into two capacitors, the first capacitor at the input, it will be dominating. The second one, basically, it doesn't have too much effect already. So it only happens, so basically Miller effects want to bring out that the capacitance effect is more obvious at the input compared to the output. So that's all for Miller's effect. Now let's look at how to find transfer function exactly. So you should given in terms of, like, I will give you a circuit. I will ask you to find transfer function. So you can use small signal model, or the other easier way is what we call finding poles by inspection. So that's the method name, finding poles by inspection. We go step by step. How do we actually find poles by inspection? How do we inspect the poles? So first thing is, I give you a circuit. So let's say it's this circuit. You need to assume that every node in the signal path contribute to a pole. So how do we define a node? As long as there's something connected to it, as long as there are two things connected to it, it is a node already. So here at V out this point, you got RD connect to it, you got transistor connect to it, you got CL connected to it. So this is for sure a node already. And then remember, we say that when we do small signal model, we have to ground VDD, we have to ground our V-in. We have to ground, not really V-in, but in this case, this is not considered a port, okay? Because this is just input. Okay, so in this case, how do we actually find the pole? The next step is find resistance from the pole to AC ground. So we say this is a pole. We want to find what is the resistance to ground. We do small signal model, we ground VDD, right? So basically now, from this pole, I can only see RD. You might say I can also see the transistor over here. There might be some R0, but let's consider it ideal. Then this part is infinity. If you don't consider channel length modulation, then this part is infinity. So we basically only got RD. And then second step is find the capacitance from the node to AC ground. So from this node, I want to find which part of it has capacitor to ground. So there's only CL. Only this CL that is a capacitor. Then you combine them. The pole, it will be 1 over RC. So the pole will be 1 over RD times CL. And finally, your V out over V in is equals to this formula. So V out over V in, generally, you can follow this red color formula. Now we only got 1 omega p because you only got 1 pole. Then you will only consider the first part. If you've got 2 poles, then you consider second part and so on, multiply together. So now we consider this part only. So we substitute. What type of amplifier is this? It's a common source, common gate, common drain. Which part of it? It looks like which type of amplifier? It is a common source because gate has input, drain has output, source is grounded. So it's a common source. So common source, we say that what's the gain? The gain is negative GMRD. So we substitute. We say that VR over V in. This is the transfer function already. Transfer function means the output over input in terms of frequency. So this A, it will just be negative GMRD divided by 1 plus S over omega P. And this omega P is basically 1 over RDCL. You substitute this one inside. So this is your final. The highlighted part one is your final answer for the transfer function. Let's examine a little bit what actually happening. What if we say that the frequency is very, 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 very low? So if frequency is very low, then my S basically is considered almost 0. Then the whole term is just negative GMRD. So it looks like your low frequency response. Like it happens at very low frequency, so it's more like your ideal operation, ideal amplifier that we have learned in common source. So it's just negative GMRD. But as frequency increases, then only we will see what is the transfer function, because then only the frequency comes into mind, and then it makes the circuit more, it affects the circuit more significantly. Then it becomes what negative GMRD divided by 1 plus S over omega P. So that's the difference. So you can have a look at this circuit first before we go to the second one. So only this part. Okay, then the next example, we got another circuit. This is a type of common source amplifier as well, meaning that input connect to maybe some resistor, some capacitor, doesn't matter. But the input basically input directly into the gate, output to the drain, source is grounded. So it's a common source. Generally, we see it's a common source, and then we substitute into the formula just now. We already know that it's supposed to have negative GMRD over 1 plus S over omega P, but we are not sure how many poles are there. So we examine the circuit. I said that poles at least need to have 2 things connected to it. So in this case, we will have 2 poles, one at the input one at the output, because at the input side over here, you can see at this point, I have two things connected, or even three things connected. So this is for sure considered a node already. So this is one pole. This is second pole. So I will have two poles. So I will have formula like this. But what exactly I should write for my WP1 and WP2, we can examine slowly. So we look at port number one, node number one. I say that from node number one, you need to see what are the resistors that you can see. So I look at the left, I can see RS. Look at the right, resistor to gate basically is infinity, because you cannot interpret any, you cannot put any electrons inside the gate, because they have the metal oxide over there. So there's only RS. So your omega P1 is 1 over RS already confirmed. And this is only C1 capacitor, so it's CS. Second one is the same as just now. You got 1 over RD and then times CL. So you have two things. You just substitute this omega P1, omega P2 over here, then that's all. But what exactly you might be thinking if this negative GMRD true? Because this is a common source, but generally common source, we do not have anything in front. We do not have anything in front. So maybe we have to check, and we have to double check whether this in front is really correct or not. Whether we can really put the gain directly to be negative GMRD or not. It's okay, we can draw the small signal model. We consider everything ideal. We ignore the capacitor, because capacitor at low frequency, basically it has no effect at all. They are basically open circuit. So we open them. We draw the small signal model. This is NMOS, so two lines on top, one line below. We got VGM, VGS. And then this RD is connected to VDD, which is to ground. At the left-hand side, usually over here, we straight away write is Vin. But now we have to write RS first, and then only Vin. Then we check what is happening. Okay, so we can say that V out. So we can say maybe negative V out over RD. Okay, the current that goes down is supposed to be equals to negative GM VGS. Okay, so this part is quite straightforward. But what is your VGS directly? VG and VS. I would say VGS is still your Vin. Why? You might say Vin is before RS. But why now, after RS, it is also Vin? It is because this circuit, you can see it is open, right? So there won't be any current flowing through. When there's no current flow, there's no voltage drop. So RS do not contribute to any voltage drop. So whatever voltage at left will be the whatever voltage at the right-hand side. So I can still say here is still Vin. So VGS is still Vin. That's why V out over Vin is still negative GMRD. So this negative GMRD still valid. Then we can start to draw the body plot. Okay, the last class we said that body plot, if we met two poles passing through a pole frequency, then the slope will be decreasing negative 20 dB per decade. So now we got two poles. We got one pole, two poles now. We got two WP. So I imagine our frequency response curve. I will have the magnitude to be Hj omega, the frequency, the transfer function, and the gain is at GMRD. We can just add it. So it'll be GMRD, but it will drop two times. The first time by negative 20 dB per decade. The second time drop more for 20 dB per decade. So it'll be negative 40 dB per decade. And then you label this is omega P1, this is omega P2. This is your frequency response curve directly. Okay, I think we have learned generally if we want to inspect by post, or so to use finding post by inspection to find transfer function. And we already learned Miller's effect, and then we already learned Bode's plot. How do we plot that? So now let's really look into different types of amplifier. Before we look into amplifier, we check our MOSFET. So this is the NMOS MOSFET. The first class we said before, NMOS MOSFET, when we draw small signal, we just assume the resistances. But actually, there are a lot of capacitance inside because it's metal, oxide, and then metal. So in between them, there might be a lot of capacitor. So we can say from gate to source, there is CGS. From gate to drain, there is CGD. From source to body, drain to body, there is CSV, CDB. From gate to body, there is CGB. So there are a lot of capacitors everywhere. Okay, you just imagine from every point to every point, there are capacitors. So if you really want to draw the circuit, okay, we say that we need a source, we need a gate to drain capacitor, gate to source capacitor, source to body, drain to body capacitor. So if you really want to draw our small signal model, every time you need to draw something like this. So it will be very complicated. Your whole small signal model will be very big. That's why we try one by one. First, we examine only common source plus resistive load. Common source plus resistive load. Okay, so let's look at this. So for a common source, with resistive load, we basically only got one transistor. So if this transistor, we will have a gate to drain capacitor, gate to source capacitor, source to body, drain to body capacitor. Generally, it will look something like this. However, we will check, is this capacitor really there? Is this bottom capacitor really there? Maybe it is not, because the top part of it is connected to ground. The other part of it is also connected to ground. So basically, this capacitor can be cancelled out. This capacitor is quite useless over here. So we're left with this one. For second one, common source plus current source load. Okay, so this one you can see, this is still a common source amplifier, but we got two transistors over here because the top one is a current source, the one we learned in chapter 2. So for all transistor, it will have 4 capacitors. So the top transistor have 4 capacitors. The bottom transistor has 4 capacitors. So we can, maybe it looks a bit complicated now, but we can try to eliminate one by one. First, we're starting from the top. At small signal model, VDD is basically grounded. So here is ground, here is also ground. So this transistor can be cancelled out directly. And then the left-hand side, this transistor at the top left-hand side, VB is a bias voltage, it is grounded. VDD is biased, so it's grounded. So this transistor also cancel out already. At the bottom also ground and ground, so this also cancel out. So I got 3 capacitor cancel out. The circuit looks slightly easier already. And we can still combine a few things some more. As in CGD2. CGD2, one hand is to be out, the other hand is to VB, which is to ground. And CDB2 also, one hand to be out, one hand to ground. So they are in parallel. When capacitors are in parallel, the capacitances added up. So we can say CDB1, CDB2, and CGD2, they can be added up into one capacitor only. So now the circuit changed already. We will only see one capacitor. These two can cancel out as well, and then left only probably 1, 2, 3 capacitor that we need to connect. So we simplify the circuit first before we really go into the whole small signal model. The third one is common drain. So common drain means input at the gate, output at the source. So this is common drain. At the bottom, I just have one current source. So again, the top part, capacitor, I can cancel out because both are grounded. The bottom part, VB is grounded in small signal because it's DC. Here is also grounded, so I can cancel this out. I can cancel this out. I left with 1, 2, 3, 4, 5. Some more, I can combine CSB2, CDB1, and CGD1 because all of them is from V out to ground. So I can combine them. And finally, your CG. Your CG is input at the source, output at the drain. Again, for capacitor, this one only can combine two parts. Okay, it's only CGD, only CSB, and then CGS. The rest cannot generally combine. Then you realize one more thing is we learn Miller's effect. So we want to check at which circuit that has Miller effect. Miller effect meaning that you will have a capacitor in between input and output. So let's check the first circuit. Yes, we have Miller effect because at input and output, I have one capacitor. So common source will have Miller effect. This one also, input to output, I have one capacitor. So Miller effect does exist. The third one, from input to output, in is over here, out is over here. So there's one capacitor in between them. So yes, that's Miller effect. But when coming to common gate, so input is over here, output is over here. There is no capacitor connected between drain and source directly. So there's no capacitor in between them, meaning that there is no Miller effect capacitor. Everything looks normal. Okay, so I think you guys can practice a while to check how many capacitor that you can eliminate in total without looking at the solution. So this is the first circuit. I want you to draw out what capacitor in the end that is left and how you can combine them. The other circuit is check how many capacitors left. Yes, so only these two. No need small signal, no need anything. Just draw out how many capacitors left in the end, how you can combine the capacitors before we go into the real small signal model. So we can have a look. This, for each transistor, there'll be 4 caps. So there'll be 1 cap, second cap, and then at the drain, it will always have a cap connect to ground. At the source, it will always have a cap connect to ground. Here also the same thing. First cap, second cap, 1 cap connect to ground. The other cap connect to ground. So let's examine one by one. This is VDD, so in the end it is grounded. So ground and ground, we cancel this capacitor. This part is V bias, so meaning that it is DC source also, so I will ground this as well. This is ground, so I can cancel this out. Over here, this is from source to ground. So from V out to ground. Here is also from V out to ground. So we name this capacitor number. So we say this is C1, say this is C2. This is also V out to ground. This is also V out to ground. C1, C2, C3, all are from V out to ground. So this one we cannot cancel out because it's between V in, V out. Here is between V in to ground. So nothing special. Here is ground and ground, so I can cancel this out. So in the end, I left with 1 capacitor, 2 capacitor. So we call it C4, C5. So C4, C5 individual one. And then we can combine C1 plus C2 plus C3 together because they are from V out to ground. That's it. So in the end, you're left with probably only 3 capacitors in your small signal model. And in this case, we again have capacitor, capacitor, so here is ground, here is ground. We cancel this out. How also VDD to ground, so we cancel it out. This is ground, this is V in, so we cannot cancel this, unlike this one. We cannot cancel this. This we also needs to remain. This is V in, V out. V out to ground, V out to ground. So we call this C1, we call this C2. Both are V out to ground, V out to ground. And this is also V out to ground because V bias is V out to ground. V bias is grounded, so C1, C2, C3 again. And this is V bias, which will be grounded. This is already grounded, so I cancel this out. So let's name this C4, C5. So again, looks like we will still have C4, C5, and then combine C1, C2, C3, because they are from V out to ground. So again, we will have only 3 capacitors remaining. Okay, so this is just to simplify the circuit before we really move into small signal models. Now we really need to look into how do we properly frequency finding post by inspection. You can already find your frequency response, but maybe if you like a more proper way, this is you can use for any methods, because the last one, if by post, maybe sometimes it's very hard for you to find the post. So this is another method, frequency response computation. The first thing is you need to draw out all the capacitor like this, and then you merge them. Second thing is you find out what is the V out over V in, and then you plot out the frequency response curve, which is the body's plot. So let's look at the first circuit. So the first circuit, you ignore the red color part. You have a common source amplifier. So this common source amplifier, it says that the first step is you have to draw out all the capacitors. So okay, we draw out because there's only 1 transistor, we draw out 4 capacitors, and then we know we can cancel out 1. Then we try to draw out the small signal model. Small signal model. So if this is the small signal model, we know that generally small signal model, when there's an NMOS transistor, I'll need 2 lines up, 1 line below, and we consider GM-VGS as the current. So from output to ground, there is RD, and then from output to ground, there is also this drain to body capacitor. So I call it CDB. In between input and output, there is gate to drain capacitor. So I call that CGD. So from gate to drain, I have a line of capacitor. from gate to source, there is CGS. So this is my general model, small signal model. Then we will examine, do we actually have a capacitor in between input and output? There is a capacitor between input and output because input is somewhere at the left, output is somewhere at the right, because this is V out, this is V in. So we do have one capacitor between input and output. So maybe from the top small signal model, I can change a little bit to be the one at the bottom, because we have learned Miller's effect. Miller's effect is state that in the end, Z needs to be, Z1 will be equals to Z over 1, Z over 1 minus A, Z2 equals to Z over 1 minus 1 over 8. So generally, we can say that we can split CGD into two capacitors. So you realize I still maintain my RS, I still maintain my CGS, I still maintain my GM, VGS, RD, CDB, but the middle part I split into two paths already. So I know at the left part, it needs to be plus. So Z over 1 minus A, Z is 1 over CS. So in the end, it's just CGD 1 plus GMRD, because this is a common source. So the A is basically negative GMRD. So now negative, negative, it becomes positive. So plus GMRD. So it's CGD times 1 plus GMRD at the left-hand side. At the right-hand side, it will be CGD 1 plus 1 over GMRD. So you can draw it out in this way already. Then we can check poles by inspection. This poles is very easy to notice. There are only two poles, one at the left, one at the right, one at input, one at output. So we can see directly. We see at the input side first. So the first port. At the first spot, what is the capacitor that we can see? We can only see RS. There's nothing else happening. There's no other resistor happening. So we can only see RS. So it's 1 over RS already. What about the capacitor? Capacitor, there are two. One is CGS, one is CGD 1 plus GMRD. They are in parallel, so we have to add them up. For omega P out, so the port is over here. What are the resistance that we can see? We can only see RD. So there's only RD, and then two capacitor in parallel, so we add them up. So you found your omega P in, omega P out. So you have two poles. So your Bordet's plot basically have to drop 2 times. One is omega P in, one is omega P out, and your gain is GMRD, because we already know common source is GMRD. So you need to write the whole transfer function. It will just be negative GMRD over 1 plus S over omega P1, 1 plus S over omega P2. Okay, I will pause it here to let you digest it if you really understand this part. Okay, so let's go into small signal model directly. The first method is post by inspection. The second method is small signal analysis. So we have drawn this small signal model just now. For small signal analysis, probably we don't even need to split the Miller's theorem. We don't even need to use Miller's theorem to split the capacitor. We can do directly. So based on this circuit, let's examine. We say that at the input side, basically, Vin minus VGS over RS, this that goes in, okay? The current that goes in, it should be equals to all the current that flows into the circuit. So what are the other current that flows into the circuit? It will just be this one. So this current go in, it will just be VGS times CGS, okay? Because we know that V over R and C, the R for your C, the impedance for your capacitor is 1 over CS. So it's just, instead of V over R, now it becomes VS, VC is your current directly. So VGS times CGS, S, okay, because 1 over CS, because we say that Z equals to resistance doesn't have impedance, so it's just R. But for capacitor, it is 1 over CS. So here it is actually V over Z, but this Z is 1 over CS, so it becomes VGS times CGS directly. So the current that flows down. And then what is the current that flows to the right-hand side? It will just be VGS minus, this point is V out. VGS minus V out over Z of your CGD. But now it is just CGDS. So you come with first equation already. Second equation, we say that the current that flows inside means negative GM VGS is supposed to be the current that flows to these two parts as well, which will be V out minus VGS and then CGDS. Okay, which will be, so the current that goes up to here, it should be the current that goes out as well. So the current that goes up is V out minus VGS times CGDS, and also V out divided by RD, V out CDBS. So you got two equations. And then I think it's good enough to proceed already. We just separate out which one is input, which one is output. So the left part, we separate out VGS. So you got negative GM. And then we see which part of it has VGS. So CGDS, we move to left-hand side. Right-hand side, we do V out. So V out CGDS, V out 1 over RD, V out CDBS. So we came up with equation number 3. So the rest is just very long maths, okay? So we don't need to go through that very detailed. But in the end, it will be something like this, a very, very complicated equation. But you will realize that you have a pattern, which is something square plus something plus something S. So it's S squared plus 1 over S plus 1 over S. So this pattern basically, it looks like this directly. So it's S over omega P plus 1, S over omega P plus 2. So in conclusion, if we just assume one pole is quite far from the other one, okay, because it ended up with, okay, so if we go through the maths, it ended up with this equation. So this equation, it gives us very complicated things, but we can find the denominator to be S squared 1 over omega P1 plus 1 over omega P2 times S plus 1. You can see S squared over here. And then 1 over omega P, 1 over omega P, S is over here, plus 1 is over here. So this term looks exactly like this one. So we can imagine if omega P1, so the first pole is very, very small compared to the second pole. Then we can also say that 1 over omega P1 is very, very, very big compared to the second 1 over omega P2. So we only need to care about 1 over omega P1. So if we only care of 1 over omega P1, that is just 1 over RC. So it's just this one. If only 1 over omega P1, we check out where is the P1. P1 is somewhere over here. So we just check this whole term down. Then we can compare these two. We can compare these two. So you realize that finding poles by inspection, you have 2 poles. Using small signal model, you also have 2 poles. So both methods are correct. And then these two equations, omega P1 and the omega Pin using poles by inspection, they are quite similar. Okay, they are quite similar, just only some part that is not very important, they added there. So generally, finding poles by inspection is correct. So now we can come out with this already. We can draw the body plot. Body plot say that it's just GMRD, and then probably it will have 1 omega P1, and then later you have omega P2. But now we focus on omega P1. So we only left with this black color curve. Then the gain is GMRD. So we draw even the body's plot already. But what exactly is your GM? GM in first class we derived to be square root of 2 mu n C of W over L ID. What if my width times 2? So this becomes 2W. Then it will be, your GM will be square root 2 GM. So square root 2 GM is more than GM. So it will go up a little bit. But if your GM go up a little bit, then you realize that 1 over something, this thing goes down a little bit. That's why your omega P1 goes down a little bit. Your bandwidth of the circuit might be reducing, because we say that it is the negative 3 dB bandwidth. So maybe initially the negative 3 dB happens at probably 100 kilohertz. Now it only happens at 50 kilohertz. It moved to the left-hand side a little bit already. So just remember, as we increase our GM, the frequency response might affect, it might go to lower frequencies. The next is a common gate frequency response circuit. Okay, so again, a common gate as in input at the source and then output at the drain. So I will stop here for a while. You guys draw out all the necessary capacitance, double check whether you understand how do we map from the left circuit to the right circuit. Yeah, you assume later when you draw small signal model, you have to map all the capacitor. How do you map that? So we combine first. Okay, so common gate, we know that there's one transistor, so we have 4 capacitors. RD, it is supposed to be grounded because up there is VDD. Here, this capacitor here is grounded. Here is Vout. Here is grounded, here is Vout. So we can combine these two together. This is gate to drain. This is drain to body. So CGD plus CDB. Body is grounded. RS over here, it will have a capacitor connect to ground. Another capacitor also connect to ground. So it's CGS and CSB. So overall, your circuit is like this. You can first use small signal model to find out what is the VR over Vin directly, the very complicated one. Or we can ignore the whole part. We go directly into finding what is the pulse. We use pulse by inspection directly. Okay, so we ignore the whole thing. We do need to do small signal analysis. But we straight away go into this. This is just a copy of just now that one, okay? So we look at first pole. We say they want to find what is the omega P1. At first pole, what do you have over here? You will have, what's the R that you are seeing? Since this is a source, the R that you are seeing is RS, but there's also one more R. Because we already mentioned, source you can see from everywhere. Source to drain, we will always have a resistance of 1 over Gm. So it is RS plus 1 over G, RS parallel with 1 over Gm is your omega P1 resistance. Capacitance is just CSB plus CGS. Pole number 2, you only got RD, and then you only got CGD plus CDB. Then you can straight away draw out the 2 poles already. The body plot shows that it will drop 2 times. However, what is the gain? This is a common drain, but we have added so many things here and there. We might need to figure out what exactly is the gain of it. The gain that we need to draw at here, it is very simple. You just need to draw out this into a small signal model. So we draw exactly the same. Gate is grounded, GM. Over here, I left only RD. Take note that when we draw small signal model to just find the gain only, we don't need to try RD. At the source, you only have RS, and then directly to input already. So through this, we have found earlier as well, the gain will just be GM divided by 1 plus GM RS. So for common gate, generally the gain is this one. So you found your transfer function. So let's compare 2 types of amplifier, common source and common gate. We've copied out the omega P1 and omega P2, both omega P1 and omega P2. You will realize that generally, if you compare only omega P1, CG omega P1, common gate omega P1, generally, if you use the same transistor type, it will be somewhere further, somewhere larger than the first omega P1. Okay, so you realize that one of it, the lower point of both, comparatively, CS1 is much more lower, CG is much more higher. So common gate has a better bandwidth than common source. So if you need to go for bandwidth, you go common gate circuit. Then second pole as well, so everything move. So basically, common gate generally has a better bandwidth than common source. Okay, the next one is common drain. So just to take note for common drain, we don't really like to calculate what is the frequency response, because generally common drain doesn't have much effect on frequency response. So if you say that, you can see that I explained everything, but in the end, we do not have Bodi's plot. It's because common drain, we can say in common drain, the CGS does not function in the circuit. The input to output CGS does not function in the circuit. So CGS will not degrade the frequency. The input to output capacitor does not degrade the frequency response. means that the amplifier had been bootstrapped by CGS. No matter how CGS changes, the output up and down is still exactly as the same as input. Just as when we derive for common drain, the gain is equals to 1. So we don't need to go through common drain frequency response because it is not important at all. Now let's do the last question before we end this chapter and we end today's class. So we cascode two types of amplifier, common source and common gains, and we assume lambda is equals to 0. So bottom part is a common source amplifier. So this common source, it acts as an input already. The whole thing acts as an input already to the top transistor. So this will be common source to cascode with common gate. So first step, you draw out all the necessary capacitor. You see which part can cancel out, and then we do the next. Okay, so take some time, try to draw this circuit first. So we can have 4 transistors in total. Okay, so here supposed to have one more to ground as well, but this we consider CL already. So this capacitor, it is connected to ground, and then one point is to the drain of your number 2 transistor. So at here we combine to be CL plus CGD2. BB will be grounded. Here we can combine CGS2, CSB2, CDB1, CGD1, but got Miller effect, so we separate them. So generally it can become this circuit, okay, because we split this capacitor into 2 parts. So this is the general circuit. How do we find the pulse? We want to find frequency response. So we use pulse by inspection. So let's find out what are the pulse. What are the pulse? It will be the first pole. We have 3 poles over here because generally here got something connected to it. Here got the other part. The number 3, it got RD and then got CL. So total we have 3 poles. Look at the first pole, it will only have RG and CGS. 1 plus CGD1, 1 minus A. We do not know what is A, but that's okay first. That is okay first. So the first pole is this part. Okay, the first pole is just omega P1, 1 over RG times whatever capacitor happening. Then second pole, how we do is, remember we say that, oh, looks like there's no resistor happening in between them. But since it is connected to a transistor, from source to drain, it will always have 1 over GM. So we call it 1 over GM2 times with CGS2, CSB2, CDB1, CGD, 1 minus A. This is the other one. The third one, you will see a pole to ground. We got RD. We do not care what happens from drain to source because it will be infinity. We out, we got CL plus CGD 2. So looks like we can have the triples directly. But what exactly is the gain? We keep on mentioning the A, the A, the A. What exactly is the A? So A is actually your common source. Because we say that the input at here, output at here. So the gain of your transistor for this A, the gain where you want to split your Miller's effect, it is only considering M1 transistor, which is P over Q. P over Q. P over Q means this part is just a common source amplifier, which will be negative GMRD. Negative GM1 is for sure, but what exactly is the RD? The RD is the output point resistance. So from output point resistance, you will only see one resistor, which is from source of M2 to drain of M2, 1 over GM2. So we can say the gain of this is just GM1 over GM2, negative GM1 over GM2. You substitute inside these two gain, then you complete your omega P1, omega P2, omega P3 already. So you can draw out, okay? So you will realize that you can draw out the first pole directly. If you compare common source only and common source cascade with common gate, you realize the omega P1 is again much more further compared to common source. So common source has the worst frequency response. Common gate is slightly improved, but when you cascade two things, the frequency improve even further. So the bandwidth improve. Okay, so that's all for frequency response chapter. And then the last chapter, it will be feedback. So please try to do again your assignment. Hold on. If not mistaken, the last class I asked you all. So who haven't got assignment groups? Yes. Again, the same question. That's okay. If you do not have any groups, if you are not submitting, I am okay to just see you again the next class anyway. The next sem, I from your group. If you do not submit before the deadline, then that's all. I won't extend for you. So again, group assignment deadline, 3rd of July. Individual project deadline, 10th of July. Your quiz, I'll probably put at the last week. I will let you know the quiz scope by next week. So because by next week, we will be almost finishing all our syllabus already. Then you have your own time to do your stuff, your assignment. If you want to ask anything related to your assignment, please come to me. You can Teams me, you can email me, but better to Teams me, like I will reply earlier in Teams, or you meet me in office, anything you like, okay? But please do your assignment. So now let's take attendance and end today's class. 的 assignment 做到怎么样了？对。